Okay. Yep. Wonderful. Hi everyone. Welcome to the 2134 crash course. Let me take a screenshot. So, first and foremost, we're looking at resonance, because this seems to be, do you need it more zoomed in? So, this is from the, I believe, 2017 paper. Yeah, so this is 2017, question 3B. So it says for a series RLC circuit, which I'll draw up like this, series, resistor, inductor, capacitor, and this is V in. We know that its resonant frequency occurs at 1 on root LC. So we want to prove that the voltage across the resistor, VR, is equal to the input voltage V in at the resonant frequency. So who has any ideas how we might start this sort of question on resonance? Any takers? So what are we looking at here? I guess let's also say that there's a current flowing through it. Anyone online got any ideas?
Eric says impedance.
Impedance, yeah. So let's have a look at the impedance, or a relationship for the current and voltage. Exactly right. So let's say that let's find an expression for the current. So I is equal to sort of the impedance equivalent times V in. So this Z equivalent is what we're worried about. Now, Z equivalent, because these are in series, it's just going to be our resistance plus the impedance of this inductor, which is J omega L, plus the impedance of our capacitor, which I write minus J 1 on omega C. Now, they've told us that the resonant frequency occurs at 1 on root LC. So we actually would like to sub that in. Once we've subbed it in, that gives us, we might have to do a little bit of playing around, but L on root LC, and this is going to be 1 on 1, C on root LC. So this is going to become R plus J into L on, that's going to be the square root of L on C. And if you flip this over, this is going to be the square root of LC divided by C. That's actually the same if we make this C the square root of C squareds, then this C and one of these C's cancel, and this square root comes out the top. And you can see those are exactly the same term, aren't they? So they're going to completely cancel. And just like we expect, the imaginary part goes to 0. So this is what resonance is all about. It's essentially saying that at some frequency, omega naught, if this is the voltage across our resistor, at some frequency, the imaginary part of our impedance will cancel out. And we call this omega naught. And at this point, the maximum voltage across the resistor is achieved because there's no impedance seen by the source from these two reactive components. So we can say that Z equivalent is just equal to R. So that means that the current is just equal to R times VI. And that means that VR is simply equal to VI. Because this is I times I beg your pardon. I beg your pardon. This is wrong. The very first thing I wrote was wrong. That's a good start. VI is equal to Z equivalent times I. There we go. There we go. So essentially what we're saying is that VI is equal to R times I. So VR is equal to the exact same thing. It's equal to VI. And that's all we need to prove. So they're not too complicated, right? It took us a little bit of reshuffling and this subbing in of omega equals 1 on root LC to prove this. The other way is true. If you got asked to prove this, you would just derive this value, this expression, and show that when omega equals 1 on root LC, the imaginary part of our impedance goes to 0. Any questions or queries about that? Yeah, fantastic. Thanks so much, Thomas, James, Eric. Okay, so that's done. That's resonance. We'll have a look at transfer functions because they seem to cause a bit of grief at times. So this is part C of that same paper, 2017. And it's saying for this, I don't know if everyone can see this. We've essentially just, I'll redraw it here. Always good to have things drawn out. Very simple RL circuit, 10 ohm, 1 Henry. Our V out goes across here. And we just want to find an expression for the voltage gain V out divided by V in. How would we go about that? Any ideas? Any ideas?
Voltage divider.
Voltage divider, exactly right. This is just the voltage here. So let's first convert this to J omega, right? As a function of omega. And what's the resistor as a function of omega? If we have, essentially in the frequency domain, does anything happen to our resistor? No. Cool. So V out is going to be the impedance of our 1 Henry inductor divided by the total impedance. And then we multiply that by V in. So this is a function of omega, as is V in. So we're not told what V in is. So then the gain, V out divided by V in, is given by J omega on 10 plus J omega. There we go. Part I, done. Not too bad, right? It was just a quick and dirty voltage divider. Now we want to sketch the magnitude response. This is part I, magnitude response. So how do we find the magnitude response? Let's call this H of omega. So this is a complex number, right? How do we find the magnitude of a complex number? So let's imagine this is sort of H in its general form is like A plus JB on C plus JD. Then if we want the magnitude of H, we have a nice formula where this is actually the magnitude of the top on the bottom equals the magnitude of the top taken by itself divided by the magnitude of the bottom taken by itself. So we can say that this is just square root of a squared plus b squared over square root of c squared plus d squared. So magnitude of the top. We don't even have an a. It's pretty easy, right? It's j squared omega, omega squared, and then take the square root. It's just omega. So we get omega, and then on the bottom we get our nice square root of 10 squared plus omega squared. This might look not particularly pretty, but we just need to know what happens at a few key values. So let's sketch it like this. I'll make it a bit bigger. We're going to sketch it versus omega. What happens at omega equals 0? So if you wanted to write this out, you could say the modulus of h of omega evaluated at omega equals 0. That's what this big line means. It's equal to 0 on 10, right? Which is just 0. So we're going to start off down here. What other values could we try? Any ideas? Anyone online got any ideas? Not quite, Nikki. So yeah, we were looking for 0. Yeah, sure. All good, all good. Let's have a look at 1. Yeah, actually, good idea. Let's have a look at what happens as omega approaches infinity. So modulus of h of omega. Sorry if this is a bit small, but I think the picture is the main thing. So as omega approaches infinity, we can sort of work our limits out here a bit, right? Omega squared is going to be way bigger than 10, like that's 100. This is going bigger and bigger. So this is pretty much just going to be omega squared square root becomes like omega. So omega divided by omega, it's going to get close to 1, right? So that's our horizontal asymptote there. And then to figure out what's going on in the middle, so that approaches 1. In the middle, why don't we plug in another thing you might like to do is, say if we got asked to find the half power points of this, right? That's something that could happen. How would we go about finding the half power points? Can anyone remember the process for that? It's not in the question, but I think it's good practice. So it's sort of a bit of a different idea to what we've been doing. At the moment, we're just subbing in values of omega. Now we're trying to find a value of omega where the modulus is 1 on root 2, right? So we want to solve for this value. So why don't we say omega on root 10 squared plus omega squared equals 1 on root 2. So then omega squared on 10 squared plus omega squared is equal to 1 on 2. And then this is just going to turn into a simple equation to solve, right? So 2 omega squared is equal to 10 plus omega squared. Omega squared equals 10. So then omega is plus or minus 10. So at 10, it's 1 on root 2. That gives us another point. We could go for some more here and just plug them in with the calculator. I'll let you guys look after that. Essentially, it's going to look something like this. That's our magnitude response. So it's not too bad. Essentially, we just need to know what's happening at 0 as it gets bigger and the points in the middle. Any questions or queries around that one? Anybody online? Yeah. Or 1 on square root and slows down alpha. Well, it's, yeah, I guess the question is why doesn't it do something like this, or like, you know, more confusing things? Sub in some more values and find out. In an exam, Just go for a smooth curve, I think. Yeah, no worries. How many points on the graph? That's a good question. I would think, I'll just share this. For these questions, I apologize, just having a look. Probably 2 or 3 points. If you had 0, infinity, and maybe a couple in the middle, I think that'd be fine. It's just a common point, Nikki. So the question was, is there a particular reason we need to find just magnitude equals 1 on the square root of 2? That's just like our half power point. That's how we define bandwidth. So that would be why we'd use that. You could also just do 1. Like if we plug in omega equals 1, then this is 1 on, it's pretty much like 1 on 10, right? So that's 1 on 10. Yeah, just plug in small points. I don't think you need to worry about it too much more than that. No worries. Hopefully there's no more questions to worry about there. Alrighty, let's have a look at the next question. Okay, cool. So here is a Fourier transform question. So commonly you'll sort of get question 1 of your exam might be power, question 2, Fourier transform, question 3, some form of resonance, question 4, wildcard. Have a look through the past papers, but this is a very common example that we might see. So let's just have a look at this part A. This is from, oh, I forget what year. What did I write? 2017, semester 1. So it says, consider this function f of t, and we want to determine the RMS value. So the RMS value, what are we looking at? What does RMS stand for? Any ideas? Root mean square. So even though it's RMS, we do it in the reverse order, right? We square it, we take the mean, we take the square root. So our f of t is a periodic function. So when we take the mean, we can just worry about from essentially over one period. Let's square this. So f of t, if we write it out, is 0 from 0 to 1. It's 1 for 0 less than or equal to t less than or equal to 2, and 2 2 less than or equal to t less than or equal to 3. So if we do f squared t, essentially these just get squared, right? So it's going to be exactly the same when it's 0, 1, it's going to be that, and then 2 squared becomes 4. It's going to equal to 3. And then let's take the mean. So the mean is essentially just an integration, right? We're taking an average, which is a sum. So if we take an integral from 0 to 3 of f squared of t dt, this is going to be equal to integral from 0 to 1 of 0 plus integral from, so that's 1 to 2 of 1 plus integral of 2 to 3 of 4. These are like, pretty easy integrals, right? So that one just goes to 0. That one's just 1. And that one is 4. And then we take the root. So the square root of the integral of f squared is just going to be root 5. Oh, that's not 5. I believe I'll just double check. 1 on 3. Oh, I beg your pardon. So this is the integral. So this is the sum, but for an average, we've got to divide by the period. So that's what I missed as well. So we would need to divide by the period. We've taken the period to be 3. So then let's divide this by 3. So this would be the square root of 5 on 3. So that's our RMS value. Not too bad. Any questions there about the working? Yeah?
Peter, can you just, they're asking if you could zoom in on the question.
Yeah, absolutely. I can try and write it a bit smaller. These are, yeah, like, be prepared to do a fair bit of working. These do take some writing, but hopefully it's manageable. So we've done this part I, we've taken the RMS value. Now we're looking for the trigonometric Fourier series up to the second harmonic. So maybe if everyone wants to quickly jot down the question or take a screenshot or something, because there's not a whole lot of, oh, actually, I might be able to work here. So remember from before, we've got this expression for f. So that's essentially just another way of describing this for each period. So we're really only worried about each period, right? So I'm going to choose this section as defining one period of my series. So for Fourier series, we know that it has to be periodic to be able to use it, and we've got that. We assume it keeps going on forever. So we know. Can anyone tell me what A0 is? It's 1. How did you figure that out?
It's just the area under the curve divided by period.
Yep, exactly right. So our period is equal to 3. And the area under our curve, we can just think about it in blocks, right? So this is going to have an area of 1. This is going to have an area of 2. So A0 is equal to 3 on 3, which is 1. Cool. And yep, we can double check that over here. So A0 is 1. These are also just integrals, right? So now, AN. We've got, apologies for that. We've got an expression for it that's a bit nasty looking, but 2 on t integral from minus t half to t half, or this is the same as 0 to t, so let's use 0 to t. And then essentially we just multiply our f of t with cosine. Now remember, AN is to do with cosine. So that's why we multiply by cosine here. Cos n omega naught t dt. So if our t naught is 3, what's our omega naught? Any ideas? Do 2 pi on 3, yeah. Cool. So we do 2 pi divided by t naught, which is 2 pi thirds. Cool. So now we know what our omega naught is. We know that f of t is like fairly well defined and quite easily defined. So let's just write this out as 2 on 3, that's our t. And then we're going to have an integral from 1 to 2. It's going to be 1 times cos n omega naught t dt. And you can just leave that as omega naught while you're working it out. No point subbing in 2 pi on 3 and getting confused and flipping things and all that. Better to just leave it in its most abstract form while you're doing this stuff, and then you can sub it in later. And then we have the exact same thing, but we double it for between 2 and 3. And then that's 2 cos n omega naught t dt. You've got to be careful with this, but it's not super difficult integration. We've done sine and cos a lot. So 2/3, we're going to go for cos goes to minus sine, and we're going to divide by this. It's between 1 and 2, and then 2. I beg your pardon, not sine. Derivative of sine is cos. Yep. Sorry, not negative sine. And then 2 on n omega naught sine of n omega naught t from 2 to 3. Any questions or worries with the integration? The answers on the right for Bn and An, why do they not put the coefficients of t over 1? So, yeah, here I've just got the answers that were supplied. The coefficients of t over 1 for the antiderivative. Two pi. Not quite sure what that means. Yeah, no, all good, Thomas. I'll come back and have a look in a second. Oh yeah, true. So then we should be able to just simplify this out, 2/3. And then this is going to be 1 on n omega naught into sine of 2 n omega naught minus sine of n omega naught. Yeah, actually, this does seem weird. There's no pi's coming out when there should be. Anywho, and then plus 2 on n omega naught into sine of 3 n omega naught minus sine of 2 n omega naught. yeah, and then we can plug in our values of omega naught and n. Yeah, this seems weird. I'm not sure why there's no highs coming out. So I guess then we would sub in our omega naught, so 2 pi on 3, and we can also sub in our n values. So A1 is equal to 2/3 of 1 on n, well, n is 1, so just 1 on omega naught into sine of 2 times omega naught minus sine of omega naught plus 2 on omega naught sine of 3 omega naught sine of 2 omega naught. It's easy to get into these sort of messy situations. Try and keep it as clean as we possibly can, I guess. But sine of 4 pi on 3 so when we follow through this working, that's going to be 2 pi on 3. Yeah, feel free to go through these questions as well. But we should be able to find that A1 comes out as 0, and then same for our A2 value. And that's just going to be through substitution. Just double check these integrations are okay. Very strange. Yeah, so this one's going to go to 0 because it's 3 times 2 pi on 3. So that goes to 0, and then sine of that minus sine of that. 4 pi on 3. Yeah, so we should be able to simplify this down to get an expression like this. But I think with some extra pi on n's, because it seems there's not been divided through by 3 on 2 pi. Yeah. Cool. Okay, so that's AN, and then BN, same difference, but we're going to be multiplying by sine. And we should be able to obtain a similar result with these answers. I'm not super convinced by this, and I don't want to waste too much time on it. Definitely just go through and check answers. Yeah.
You know how much work you need to show?
these questions. Like
For these sorts of ones?
for this one, I can imagine the meters are all working, but for simultaneous equations, that sort of thing, you reckon they do all work as well?
Do as much as you think illustrates the point. But yeah, for these sorts of ones, just try and be methodical with it and not get wrapped up in it. That can be an easy, like even what's happened to me, like it's easy to fall into the trap.
Can you just say from the beginning that AN is going to equal 0?
That's another option as well. So if you can prove that it's odd.
So you have to show the word.
That's, yeah, I don't know. Like, I'm not going to guarantee anything.
Yeah.
But I think if you have the understanding that, well, this is an odd function, so AN will be equal to 0. But I don't think it is an odd function. I think it just so happens that those first two. Because an odd function would look something like this. Right? I think. It's odd symmetry. And then even would look like this. It would be like flipped in the x-axis.
Yeah. So this is not an odd.
Exactly right. It just so happens that those first two come out as 0. So again, that's why we need this integration. And what we should start to see, as in the what the answers supply us with, anytime you see a 2 pi n, so sine of 2 pi n, no matter what n we have, right, if we have 2 pi, 4 pi, anything, that's going to be equal to 0. So we can immediately just chuck that term. And same for pi n even. So if you had sine of pi n, that's just going to be equal to 0 for all n. Because that's 0, pi, 2 pi, 3 pi, 4 pi, always 0. And then same for cosine. And then you should be able to get a bit of a neater expression to then sub into. I don't recommend trying to sub into big expressions like this. But yeah. So that's how we would do that one. I apologize for the messy working. We'll just go with what's on here. But I do think that there should be like this should be divided by whatever this is, I think. But other than that, the working looks good. And then, yeah, I guess that's that question. And then we want the Fourier transform of this function. So this is not a Fourier. We can't just expand this with Fourier series. Does anyone know why we can't just expand it with Fourier series?
Not periodic.
It's not periodic, exactly right. So non-periodic. So if we've got a non-periodic function, we have to use this bad boy, and in particular this one. So we want x of omega is that fun integral. So I'll bring it over this side. So there's our question B there. Sorry if it's a bit small. And it wants us an expression for f of omega. So let's say f of omega is going to be integral from negative infinity to infinity of f of t e to the minus j omega t dt. So because it's always, f of t is 0 outside the interval alpha beta, this just becomes an integral from alpha to beta. And then it's just 1, so it's just e to the minus j omega t dt. So we know how to integrate e, just treat j as a constant. So this is going to be minus 1 on j omega e to the minus j omega t from alpha to beta, which is equal to e to the minus j omega alpha minus e to the minus j omega, sorry, beta minus alpha. And then we're going to divide that by j omega. There are some further simplifications that we can do, but this is okay. Like, you can get away with this one. It's still an expression for f of omega that you could plug in an omega to. And I'll just have a look at how the best way to simplify it would be. Just bear with. Yeah, so there is, you might see in the answers that there's a complicated expression involving the sinc function. Essentially what that does is we pull out a common factor of e to the minus j omega, and then alpha plus beta on 2. And then we get e to the minus j omega into beta minus alpha on 2. So when you sub these, that essentially as you expand these out, this plus this would give you beta. So this is e to the minus j beta, and then we would subtract I beg your pardon. That would be positive. And then we would subtract e to the j omega, e to the minus j omega beta minus alpha on 2. And then we could multiply this by 2 and move this to on 2j. So this is complicated stuff, but essentially what we're doing is we're trying to massage this into having some form of a sine looking thing. So remember, sine of some theta is equal to e to the j theta minus e to the minus j theta on 2. So a common thing that we do when we get a sum or difference of two exponentials is to pull out something that so that we can get an expression of this form. So you can say here our theta is beta minus alpha on 2. So we've got e to the j omega beta minus alpha on 2. Sorry, it's omega times that minus that divided by 2j. Yeah, exactly right. So James online has got it. This turns into something called a sinc function. a sinc function. So sinc is essentially sine of x divided by x. So, excuse how messy this is. We can essentially turn this, if we again mess with this, so this is just a pure E. So we're not too worried about what's happening with this E. This is just going to affect the phase. For the magnitude, why don't we multiply through by beta minus alpha and then divide by beta minus alpha. And I might just move this all over a bit. Sorry guys. Sine of x on x. So we can say that this is e to the minus j omega alpha plus beta on 2 times by 2 on omega times beta minus alpha on beta minus alpha. And then we multiply that through by, let's call this sine, right? Because we've said that that's sine. So that's sine of omega times beta minus alpha on 2. And we want to massage this to be a sinc function because we've got this omega on the denominator. So we've got sine of something is almost that something. So if we take, if we essentially put the stuff that we want on the denominator, so we've got omega times beta minus alpha divided by 2, we get e to the minus j on alpha plus beta on 2 times this beta minus alpha times 1 on, well, sine of omega into beta minus alpha on 2 divided by omega into beta minus alpha on 2. So this becomes our sinc. Sinc has quite an interesting shape. It sort of looks like a bouncing sine, like this. So if we were to sketch the magnitude of this, if we take a big magnitude, this has no magnitude because it's just a phase. So we're just going to multiply beta minus alpha by a sinc. So I apologize for that poorly drawn thing there. There we go. So this here has a height, because remember the limit as this goes to 0 would be 1. Then we're just multiplying that by this number, beta minus alpha. And we have essentially each of these occurs at 2 pi on beta minus alpha when we set, essentially this has this is 0 every pi. So omega into beta minus alpha on 2 equals n pi, where the zeros occur at. So then that occurs at omega equals 2n pi on beta minus alpha. And so this seems like a very involved question, but now that you've seen it, you know that for any single square wave, right? Any single square wave, with alpha and beta, sorry, not square wave, square pulse, you're going to get a sinc function come out. And it's going to have a value of 1 and zeros at 2n pi. So now you can actually, you know, if you get something like that in your exam, you know what to do. Any questions, or anyone online got any queries? I apologize, that's a really long question. Probably a bit brain dead. No worries. Alrighty, let's have a look at something different. Yeah, okay, we've sort of already done one of those. Okay. Let's do some power. Who's feeling some power? No worries. This is question 1 of 2018 paper. We've got a parallel circuit, and we want to have a look at what the admittance is. So we're given that the frequency of the source is 15.9 hertz. So then omega for our circuit would be 2 pi on that. Calculator.
Isn't it just 2 pi?
Oh, 2 pi if I beg your pardon. Thank you very much. So 2 pi times 15.9, we get 100 rad per second. So this is J omega L. Admittance is 1 on the total impedance, which is actually, we can look at the sum of these here, because remember these are in parallel. So we can actually look at this as 1 on Y inductor plus 1 on, oh, I beg your pardon, not 1 on, just Y inductor plus Y resistor. Yeah, and if we work those out, we're going to get these values, 0.447 angle minus 26.6 degrees. That's not too bad. So for phase angle between Vn and In, we know that theta V equals 0. Theta I is just going to be, well, we need to do a bit more working. So when we think about our voltage and current, we know that V in is equal to Z I in. So then V in divided by I in is equal to Z. So if we want theta V minus theta I, that's actually the same as taking the phase of V in on I in, right? Because we do the angle of V in minus the angle of I in. So we can say that that's the same as finding the angle of our Z. Now, we know that the Y is given by this. So if we do 1 divided by that, what's going to happen to that angle? Any ideas? Anyone online got any ideas? 2018 question 4BC. Yep, we'll jump on it. Thanks, Nikki. So, if we take 1 on this, that's essentially just going to put a positive sign in front of our angle, right? So this is just going to be 26.6 degrees. So try not to do any more work than you need to do, right? I didn't even need to know what the current was to find this theta V minus theta I. It was just the angle of the impedance. Moving on from there, it wants the total power factor. So, power factor, what is it? Cos, easy. Not sure what that comes out as, but it's something like 0.894 as a value. We can see that there was going to be a mark loss. What are we missing here?
Lagging.
Lagging. Why is it lagging?
Because the voltage angle is like ahead of it.
Exactly right. This is a positive angle, isn't it? So that means that theta V is, even though it's 0, this is theta I is a negative value. So this voltage leads, current lags voltage. So if I lags V, PF is lagging.
Also, there's no capacitor. So
Yeah, exactly right. We know that inductors are always going to have a lagging power factor. It gets a bit more confusing when we've got both. We don't know which way it's going to turn. But here, it's pretty obvious that it's going to be lagging, and it's proved by the maths. That's good. That's what we want. Next question is to sketch the power triangle. So, what parts have we got in our power triangle? I'm going to draw it pointing upwards because it's a lagging power factor. What's on this axis, the average power P? Perfect. This angle is theta V minus theta I. What's on the other side? Q. Okay, what's the name for Q? Yep, wonderful. Q is reactive power. What's the magnitude of this called? Apparent. And what's its value in terms of V max and I max?
Max times I max.
Careful, divided by 2. Or, if we take these as RMS values,
VRMS.
yeah, VRMS times RMS. Perfect. And the reason that makes sense is because these RMS values are Vmax on root 2. So when you multiply V and RMS, the two root 2's turn into a half. So we should be able to, with this configuration, find all the values that we need. We found that this theta is 26.6 degrees. We haven't found Q or P yet, so we probably do need to find the current. We were a bit tricky in this question and just found the angle without actually finding the current. But let's say that I is equal to V on Z, which is V times Y, which is essentially this doubled. So 2 times 0.894 angle minus 26.6. So now we can fill this out. So S is going to be V max I max on 2. So it's going to be And remember, V is equal to 2 angles 0 degrees. So this is going to be 2 times 0.894 on 2, which is 0.894. I'll just double check. What have I missed? Uh, 2 angles 0. Two times. Apologies. Just trying to make sense. This power factor. Half times that times that. I'm not sure why we're getting a different value here. But let's try and work out our p value. So we should be able to do that.
Does it ask for?
Yeah, so it says to clearly label the real, reactive and apparent power and any relevant angles. So we pretty much have to do the whole lot.
Is this just a part of the complex power like S?
Yeah, so that's another option. So we've got the actual complex value is 1/2 times the phasor V times the phasor I complex conjugate. So that would be 1/2 times our 2 angle 0 degrees. And then times by 0.894 angle 26.6 degrees. Yeah, still not sure why this.
One says it might be
I think I forgot to divide by 2 in the solutions.
Yeah.
I was looking through it as well. Yeah, the solution is wrong.
Yeah. I'm glad I'm not going crazy. Cool. So if we divide by 2, we should get this 0.894. It's not RMS. This is just the actual value, and then we can use that to find P and Q. So this is equal to mod S cos theta, and this is mod S sine theta, just by simple trig. So mod S cos 26.6 degrees, 0.092 watts. And mod S sine of, oh, sorry, wait, I had my calculator in the wrong setting. Yeah. 0.8 watts here. And then for mod S sine theta, we get sine theta 0.4. And so this is in watts, the real average power. What do we get for Q and S? What are our units there?
It's Q VAR.
Sure, so what does VAR stand for? Volt ampere reactive. Wonderful. And how about S? What units does it have? Yep. So this is going to be in volt ampere. Nice. Okay. That's all it wanted us to give it. So we're done. So we've sketched the power triangle with all the different values. And now it wants us, if we zoom back in, sorry, my laptop's died, but that's fine. Yeah, if there's a charger around.
Yeah.
So now we want the type and value of the circuit component which, when connected in parallel, will raise the total power factor to unity. What sort of component are we going to be adding here? Yeah, capacitor, right? So we chuck our cap like this, because our triangle at the moment is pointing upwards, like this, and we want to bring it down, all the way down, so that it becomes just a line with zero reactive power. It says raise the total power factor to unity. It's a bit of a trick question, right? It's not raising it, it's lowering. Oh, I beg your pardon. It is raising the power factor, but it's lowering the reactive power. So we know that our Q old is 0.4 volt amps reactive. So this is where we're starting, and we want Q new to equal 0 volt ampere reactive, right? Because if we have 0 reactive power, our power factor is going to be 1. So looking at that, that means that our Q difference is equal to 0.4 volt amps reactive. And what we're saying is this has to be supplied by a cap. So this is supplied by our parallel capacitor. So we know that just like P is equal to V squared on R, Q can be written as V squared on X, where in this case it's going to be the reactance of the capacitor. This is RMS as well, just to be careful. So we can solve this equation here for XC. We know that XC is the same as 1 on omega C. So then we can just flip it and say C is Q on omega V RMS squared, and then just go through and solve. Not too much to it, right? So once we can get this reactive power, that's going to tell us everything we need to know just by this formula. And if you're confused about where this formula comes from, just think of it as very similar to the power one, but for a reactive component. And yeah, I guess we can plug in some values. So 0.4 on omega was, we said it was 100, right? Something like that. 100, and then our V squared is just going to be 2 on root 2 squared. 100 times 2 on root 2 squared. 0.00. So that's yeah. That's that. Any questions about that one? Yeah, sometimes these solutions might not be 4 millifarads. That was using 0.8, we were using 0.4. Yep, that's fine. And you will get carry-on stuff, like if you've got a different value for Q, but you calculate the capacitor based on that, that's chill as well. Cool. Alrighty. I think there was a question about some of them. What was Vicky? Have you looked at it? Of this one? Okay, let me see if I've got it. Screenshot. How do you find Q nu if the power factor isn't 1? Okay, yeah, good question. Good question. So I did miss something. So here I've said Q nu is equal to 0. That was just, I should have drawn the new triangle. So this is old triangle. The new triangle, let's say the power factor nu, let's say power factor nu was 0.95. Then our new triangle would be a sort of shrunk down version of our old one, where this theta equals cos inverse of 0.95. So what you would do to answer the question is you'd first find what theta nu is, because you know what the new power factor nu is. And then we're going to assume that P stays the same. And if P stays the same, then Q is equal to P tan theta nu. And that gives us Q nu. So that's all that you would need to do if the power factor wasn't 1. But here they've told us that PF nu equals 1. So theta nu would be 0 degrees. Cool. Okay, good question. Sorry about that. Laptop's kind of done. So question 2018, 3 and 4.
Question 4B and C.
4, B and C. Yeah, cool. Okay. So 4B is saying f of t is equal to, yeah, my laptop's not having it, that's a shame. Delta of t minus 1 plus delta of t plus 1. We want f of omega. We're going to use the exact same expression that we always use. Integral from minus infinity to infinity. X of t is going to be delta of t minus 1. And I'm going to actually break this up into 2 right off the bat. So you can think they've just been summed. I've broken them out into 2 integrals. Does anyone know what the property of the delta function is when it's inside an integral? What does it do?
Opposite sign.
Sure, so it essentially samples this function. So if we have some, this is going to be delta of t plus 1. This is going to be delta of t minus 1. E to the minus j omega t, we don't really know what it looks like, right? It's some complex number. But what we can say is this is going to essentially plug in 1 into this function. So this one here just becomes e to the minus j omega 1. And this one here becomes e to the minus j omega minus 1. So this is, yeah, e to the j omega minus e to the minus j omega, which we could write as sine, right? You've got 2 exponentials, they got the same thing. This would be 2j sine of omega. So that's f of omega. Part B.
For someone's sake, why is it negative?
Why is what negative?
So it went from plus to minus.
Oh, I beg your pardon. Yeah. Thank you. Yep. So that would be 2 cosine. Because if we sort of divide this by 2 times it by 2, we get 2 cos. Yep, thanks. Good find. Whoever saw that. Then part B, I'll just grab it up what I'm looking at so that I don't spend too long on this. So what properties do we get given? We don't get given any properties, but I would recommend having some Fourier, like having the properties and also the table with you. So the next section asks about a function that looks like this. And you've got like minus 2, minus 1, 1, and 2. It goes up to 20, 10. That's omega. And so we can write this as a difference of step functions, right? So this is u. So sorry. U of t will look something like this. Boom, boom, boom. So it'll jump up to 1. U of t minus 1 will be that but shifted over to here. So when t equals, I beg your pardon. When t equals minus 1, then this will essentially emulate u of t at 0. And then u of t minus 1 shifts it to here. So this is all we sort of really need to know. So this could be, let's call them like t naught. This would be minus t naught. And then if that's t1, this would be t1. So we can see this one looks sort of like that, right? So we can break it up into these sections like that. So 3 different sections. This would be, and also u of minus, this is what u of minus t looks like. So it just flips it. So we can think about this one as, this is u of, yeah, and so this is in the time domain, but same difference for the frequency domain. So we can think of that as u of omega plus 2, right? So it's, sorry. Oh, this section in here would be u omega plus 2. What's that?
Is minus u of t the same as u minus?
No, I don't think so. Minus u of t would look like this. So this section here is u of omega plus 2, and then we're going to subtract u of omega plus 1. What that's essentially saying is u of omega minus 2 starts here and then goes along like this forever, and u of omega plus 1 starts here and goes on forever. So when you subtract them, all this bit gets subtracted, and we just get that bump. And that's going to be multiplied by 10. That's like 10 times those, right? So if we had 10 u of t, it would just scale it up. Same difference in here. This would be u of 20 into u of t plus 1 minus u of t minus 1. And then this would be 10 u of t plus t minus 1 minus u of t minus 2. And then those are three different examples, and we can just use a pair for u of t. Yeah, they're quite dense. We know that u of t plus 2 sorry. U of t plus tau plus u of t minus tau has a Fourier transform pair. You may see this written like this double arrow thing. That essentially just means that they are the pair. Fourier transform pair with, sorry, not plus, minus. Minus that has a Fourier transform pair with 2 sine of omega t on omega. We can do some tricky stuff with something called duality. So you may have to use duality in your exam. And duality is the thing where your frequency domain stuff sort of looks like a time domain thing that you've already known. And if that happens, then we've got a nice we can essentially flip them. So we can say that 2 sine omega t on t has a Fourier transform pair, but we need to multiply it by 2 pi x of minus omega. Because it doesn't really matter here whether it's minus or plus. This is just 2 pi x of omega. Yeah, so this one's quite involved in terms of working. I don't think I'll have time to go through everything to do with it, sorry Nikki. But have a look through the solutions definitely. The main things are the fact that there's linearity and being able to write up your f of omega in this form is really crucial to being able to actually put it. Yep.
Could you explain the duality again?
Yeah, sure. Duality is just one of those, like, I can pull it up. It's just one of those properties, right?
Yeah.
I don't think you're expected to. You may be even expected to derive it. I can't imagine it though.
But how do you apply it in this case?
Yeah. Okay. So in this case, we know that this is true, right? So we know that in the time domain, if you have a time signal that looks like this, right, where this is tau, that's minus tau and tau, then it has a frequency domain that's sort of a sync. And what we're saying is, well, now I've got this in the frequency domain, so we should have some sort of sync thing looking in the time domain. it's going to be a bit more of a confusing. Essentially, it's a double sink, right? We can think of this as like one of those and then another two of those.
You can also do it using this Fourier transforms, can't you?
You can also just go straight Fourier transforms if you want to.
And you know what's the Parsifal's theorem? I wonder if we actually went.
Parsifal's theorem pretty much says like power in time domain, and you can also find, pretty much you can find power in frequency domain. So that's why the square comes out.
It's a conservation.
Yeah, exactly right. Like they're just different domains, right? The actual power that you have in your circuit shouldn't matter on what sort of method you use to analyze it. So what it's asking for is like the work over a 1 ohm, a 1 ohm resistor, and we take F squared because it's like it's power, right? And what it wants you to show is that this integral from minus infinity to infinity of F squared of t dt is the same for mod of F omega. So these squares essentially complete the same job. The actual derivation is in the solutions. Essentially what we want to do is we can turn this, like use f of t is equal to minus infinity to infinity of f of omega, right? And then we're going to sort of extract out those f of omegas. Yeah.
Okay, thank you very much.
Yeah, it's sort of just one of those things where you got to memorize. Best of luck with the midterm, everyone. Thanks so much for coming. Hopefully that helped a bit with anything you needed. Yeah. If you've got any more questions, Lisa? No worries. Thank you. Thank you, everybody online. Thanks so much, Eric. Thanks for coming. Recording we'll send out, we'll probably put it on the YouTube channel. And yeah. Wonderful. Thanks so much, everyone. I'll stop the recording.